Today we're going to continue our work through Chapter 1, and here we go. Let's jump right into it. Today we're going to talk about the three states of matter. These can basically be differentiated if we look at two different things. Shape and volume. Alright, so if we take a gas, we're going to write S and V over here. What type of shape does a gas have? Essentially no shape, so it has indefinite shape. We're going to say indefinite shape. And its volume, again, if we were to have a small amount of gas and open up that container, what's going to happen to that gas? It's going to fill whatever container it's in. Alright, so a vial of perfume, you have some gases in there that is what you smell, and you open that perfume in the middle of the room, what happens? Eventually you can smell it all over the room. So the shape is indefinite and the volume is indefinite. If we go down here to a liquid, so we have S and V again. Shape, what about the shape of a liquid? Does it have a definite shape or indefinite shape? Again, whatever container you put it into, it takes the shape of that container. So we can say that a liquid has indefinite shape. But if we have 500 milliliters, let's say, in a flask, okay, so it's kind of, what would that shape be? Not cylindrical, not pyramidal, conical, okay, so it's conical, you pour it in a beaker, its shape has now changed, but you still have 500 milliliters of water, so its volume is definite. So indefinite shape, but definite volume. In solids, because they're solid, they definitely have a definite shape. Okay, their shape doesn't change unless you like hit it with a hammer, but generally a solid has the same shape, and it also takes up the same volume because its shape is not changing, its volume is not changing either. The other thing to look at in these pictures, we have, like, I don't know, this is like a funky old picture from the 1940s or something, but we have water molecules apparently, because if we look at our microscopic view of what's happening, we have some steam forming, alright? And steam is basically water vapor, and if these are water molecules, we have an O and two H's, and there's a huge distance between our molecules. There's not much in this little picture, but if we have a gas, there's great distances between our molecules. As things begin to slow down, they condense and turn into liquids, alright, as the temperature decreases. In liquids, you can see they're much closer to one another, but there's no real specific shape that they're taking in relationship to each other, alright? So liquids, they flow around each other, these molecules can slip past each other, they slide by each other, and again, if we continue to cool this liquid, it condenses, I'm sorry, it doesn't condense, it freezes into a solid, so that these particular H to O regions are kind of locked into place, and we have a solid, alright? Next slide. Physical or chemical. Changes can be either physical or chemical, just like we can have physical or chemical properties. A physical change does not alter the composition or identity of the substance. The easy way to think of this is begin, whatever we start with, equals end. And really we're talking about that molecular level again, okay, or a microscopic view. So ice melting. What do we have when we have ice? We have H2O, and it melts. Alright, really we have H2O, we're going to put a little S here, solid. And it melts, and we now have a liquid, but what do we have? We still have H2O. Alright, so what we start with is what we end with. If we have sugar over here, we have some sort of C6H12O6, and we have H2O. Alright, it happens that this thing is a solid and water is a liquid. And what happens is, over here, we really just write it C6H12O12, I'm sorry, C6H12O6, and we changed our little writing back here to say aqueous, and all that means is dissolved in water. So again, what we start with is what we end with. We could boil the water out and we would get our sugar back. Okay? Chemical changes are a little bit different. In a chemical change, the composition of our substance or substances are altered. Alright, and a great example of this is the combustion of hydrogen. Alright, so here is kind of a molecular view of what's happening if we have some hydrogen and we light it on fire in the presence of oxygen, or just in air, because there's plenty of oxygen in air. But really what we start with is we have some H2 molecules. We have 2 of them. Alright, so in our equation we might have 2H2. And we're going to add an O2. And then they are going to react to form. What do we form? We form waters. A balanced equation is going to say we have 2 waters, but again we have H2O, and we have H2O. So in this reaction we start with 3 different elements. We have 2 hydrogens and an oxygen, and we end with 2 compounds. Alright? We might say we have 2 different types of elements, and we end with a compound. But regardless, we begin with one thing and we end with something else. Extensive and intensive properties. These are just other properties we can use to explain compounds or elements. An extensive property of a material depends on how much matter is being considered. Okay, so extensive properties we might just summarize as size matters. Okay, so what are some properties of matter where size affects that property? And some obvious examples are just in thinking of extensive or intensive. If you have a small piece of this and a large piece of this, what things are changing? Okay, so we might say what's changing? Volume is changing. So volume would be an extensive property. The small one has less volume than the large one. Volume is basically based on length, width, and height. So we might just say length dot dot dot. Okay, so length, width, height. That's how we get volume. We could also just go to 2 dimensions and say area. But those are pretty much things that depend on size. Conversely, intensive properties are things that does not depend on size. So whether you have a small piece and a large piece, it doesn't matter. The property is the same. So things that are intensive might be color. Alright, they might be density, which leads us to another extensive property up here, would be mass. A smaller piece would be less massive than a larger piece. But the density, this ratio of mass to volume, stays constant. Okay, so color, density, it doesn't matter if we have a little piece of ice or a large piece of ice, it's going to have the same melting point. There's going to be MB, you might say freezing point, melting, why did I do a B here? I'm not sure what that is. MP, FP, you might do boiling point, but all these things, melting point, freezing point, boiling point, condensation point would be the opposite of boiling, but all these properties of these phase changes are intensive. Alright, matter. We've had this definition in our vodcast 1.1, but anything that occupies space and has mass. So mass is the measure of the quantity of matter in something. And notice the SI unit, and all SI means is the fancy word for metric. Alright, it stands for Système International, which is the French hoity-toity way of saying metric. Alright, but mass is measured in kilograms. The SI unit is kilogram, and it's weird because it has this kilo in front of it. All the other SI units are just seconds, kelvins, meter, but for mass it is actually kilogram. Alright, and really it comes down to most sciences other than chemistry don't really measure things in grams. We like to do things in grams because we just need small quantities of it, but most of the other sciences like kilograms, and it takes a lot of grams to make a kilogram, obviously, and a kilogram is about half a pound, so even a kilogram isn't that much mass per se, but a gram is so small compared to that, it's silly for the other sciences to really talk about stuff less than kilograms. Weight is a little bit different. If you've had physics, really pounds, which we use synonymously with mass, pounds really relate to newtons when it comes to SI units. But for all intents and purposes, because we do all of our chemistry on Earth, and we basically do it at roughly sea level, gravity, which affects weight, and it doesn't affect mass, we can kind of use those synonymously and we're alright. Okay? And really the difference is if we go to the moon, Weight changes because the gravity on the moon is less, but you still have the same mass. Okay, so mass would not change, weight does change. But we use these kind of terms interchangeably. They're not really the same, but we're going to say they're the same for this class. Alright, here are basically the 7 base units for the metric system. Most of these you're familiar with. Meter for length, kilogram for weight, time is measured in seconds. Amperes we will cover kind of towards the end of this year, probably in March sometime, when we talk about electrochemistry. So we'll get to this one. Kelvin is how we do all of our gas laws. Moles is how we count how much of something we have. And then really the only one we're not going to use in chemistry is the candela. So these 6 you will be very familiar with by the end of the year. And these are just base units. Metric system only has 7 ways to measure things. And then everything else is a combination of these 7 base units. And from these base units we can kind of make numbers bigger, make numbers smaller. Again, some of you had, King Henry died drinking chocolate milk, something like that. We really could care less about hectos and decas. So the prefixes you need to be familiar with. Pico, honestly you don't. Nano, just think of it as -9. Nano and 9 they look almost identical, but you need to know nano is -9. Micro is -6. Milli, -3. It's 1,000th of, so you might think there's 1,000 years in millennium. Centi, 100th of, okay, or there's 100 years in a century. And deci, 1/10 of, or there are 10 years in a decade. And then kilo, 10 to the 3rd. Here, kind of going this way, you kind of think of computers. But kilobytes, which you've probably never heard of because of everything's been a mega since you've been alive. But if we have 1,000 kilos, we have a mega. If we have 1,000 megas, we have a giga. And if we have 1,000 gigas, we have a tera, which basically hard drives are becoming tera drives now, or terabytes. Alright, volume is one of the, most used SI derived unit. And really a derived unit, like I said, is a combination of our base units. And a derived unit for volume, because volume is a cubic measurement, length times width times height, volume is really a cubic meter. Alright, so it's just the same base unit 3 times. Oftentimes this is kind of hard to use because, again, in chemistry you talk about things that are so small. So typically, instead of using cubic meter, you will see stuff more like cubic centimeter. Alright, and if we were to have a box that was a cubic centimeter, so that, by that, by that, we'd have a very small box. But that box would be the same volume as a milliliter. Alright? So usually if we are measuring solids, we use cubic centimeters. And if we're measuring liquids, we talk in terms of milliliters. But really these things get used interchangeably. If you watch any kind of hospital show on television, you might hear them say, we need 50 cc's of blood, stat. Alright, and those cc's is just cubic centimeter, which is just a milliliter, so they're asking for 500 milliliters of blood. But this isn't just a relationship that has to be memorized. A milliliter is a cubic centimeter. Let's see here. Density. Alright. Another equation that you've got to put to memory, and really I say that kind of loosely. The more equations you can really memorize this year, the better off you are, just because you have a grasp on the equation and how to use it. However, for every test you get, you will have an equation sheet. It'll be the same equation sheet you get for the AP test. So honestly, there's not really a whole lot you have to memorize, because you'll always have it in front of you, but you will be able to get through problems quicker if you're familiar with these equations. Alright, so density equals mass over volume. We're going to do just a quick example down here. A piece of platinum metal with a density of 21.5 grams per cubic centimeter. So I'm going to put 21.5 grams per cubic centimeter on the right, because we have density, or on the left, because we have density over here on the left, equals something, mass over volume, has a volume of 4.49 cubic centimeters. What is its mass? Okay, so its mass is on top. So how do we get x by itself? We're going to multiply both sides by 4.49 cubic centimeters. Alright, and on this side, anything over itself is 1, so we're left with x. And over on this side, if we multiply 4.49 times 21.5, we're going to get some number. I'm just going to put number here. But the main thing I want you to see is cubic centimeters are in the numerator, and we have cubic centimeters in the denominator. So they cancel out with each other, which leaves us just one unit over here on this side, which is grams, which makes sense because we want to know what is the mass. Alright? And you can do that problem if you would like, but that's how we set up a density problem. Alright, scientific notation. Again, this should be a review from Gen Chem, or from a math class that you probably had eons ago. But scientific notation, I'll put this at the top. Here we go. In your notes, n times 10 to the little n. Alright? This is how scientific notation always looks. And big N, alright, is always going to be some value between 1 and 10. Okay? So you're never going to see scientific notation looking like this. 21 times 10 to the second. That is not really scientific notation. How come? Because 21 is not a number between 1 and 10. We would put a 1 here and change this to a 3. Alright? And then lowercase n is just some value. It's either a positive or negative integer. So a whole number. We don't put 1.5 to 2.15 times 10 to the 1.5. Alright? And we can use scientific notation to either represent really big numbers, alright, such as the mole, alright, or we can have scientific notation help us represent really small numbers. And that's why we use scientific notation. Alright, and here we go. We're just going to do a couple examples. 5.68 times 10 to the 568.762. How do we change that into scientific notation? Because it is a big number, or actually we're going to go back here. We're going to have big, and over here on this side, we are going to write big has positive exponent. And down here, really small numbers have negative exponents. Alright, I like that better. Alright, so a couple examples. We have a big number. It's not super big, but it's sort of big. So we're going to change our decimal so that we're going to write this as a number between 1 and 10. So it's going to be 5.68762. How many times do I have to move my decimal place? Twice. So we're going to do times 10 to the second. And then our question is, does it need to stay positive 2 or minus 2? It's a big number. It's going to stay positive 2. Alright. So another example. Oh boy, it's over here on the right hand side. I'm going to rewrite it. 0.0000772. Alright, so again, we need a number between 1 and 10. So I'm going to move my decimal 1, 2, 3, 4, 5, 6 times. So I'm going to have 7.72 times 10 to the 6th. But oh, it's a really small number, so it's not really positive 6, but negative 6th. Alright? And that is how you set up scientific notation. Alright, addition or subtraction. So here we go, a couple steps for this, but here's our two numbers. The first thing we're going to do is we are going to write each quantity with the same exponent in. Again, you get your calculator for the majority of the AP test. On the multiple choice, the 75 questions, you don't have a calculator. And it's fair game to do any kind of math. It's supposed to be easy math, stuff that you can do in your head or with a scratch sheet of paper, but you will kind of have to estimate logs. Scientific notation is fair game, so kind of have an idea of how to do this without a calculator. Alright? So 4.31 times 10 to the 4th and 3.9 times 10 to the 3rd. So really we're going to change this to 0.39 times 10 to the 4th. Alright? And now that I've changed it, we can just add these numbers right up. So 4.31 plus 0.39 equals 4.70. Alright? And because we're adding, we're not going to do anything with our exponents. It's just going to stay times 10 to the 4th. Okay? And there we have it. New answer. Multiplication, and then we're going to get to division here in a second. So now we're going to multiply our two numbers together. So we're going to take 4 times 7, and we get 28. Times, And now we're going to add our exponents. So negative 5 plus 3 is negative 2. Okay, so far so good. However, is 28 a number between 1 and 10? It is not. So really, it's going to turn into 2.8. Okay, I'm moving my decimal one place. So times 10 to the, it was minus 2, but I made it a little bit smaller, so I had a bigger number. So I'm really going to add 1, or turn it into the negative 1. Okay? And if we do some division, we are going to divide n1 and n2, and then subtract the exponents. Alright, so here's our last thing. So we have 8.5 divided by 5, and that turns out to be 1.7 times 10 to the 4 minus 9, which would be negative fifth. 1.7 is between 1 and 10, and voila, we are done.